Section 4.4 Indeterminate Forms and L'Hopital's rule. L'Hopital, the name has S in it. Well, we don't pronounce it, just so you know. We have about 7 indeterminate forms. You can look at them and see how do we handle those indeterminate forms. Indeterminate means we cannot determine the value of that limit. And we need to see how L'Hopital's rule, we use it as really a good tool to help us evaluate limits, to find or determine their values. So what we have seen before when we learned about limits, we've seen that, or we looked at 0 over 0. This was an indeterminate. We also agreed infinity over infinity is also an indeterminate. That's indeterminate forms, 2 of them. Those are the ones that we use the most. And what happens is we looked at examples like this: limit as x approaches 2 of x squared minus 4 over x minus 2. And if we try this limit, you can see this is going to go to 0 over 0, which is indeterminate. 0 over 0 is not an answer. We are asked to determine this limit, but we're saying when you got 0 over 0, we haven't determined the value of the limit. So what we did before, just as a recall, we factored this. We used the factoring x plus 2x minus 2 or x minus 2x plus 2 over x minus 2. Then simplifying, then I'm just simply need to find the limit of x plus 2, which is 4. Now I determine the value of this limit. This was easy because I was able to factor out. What about if there's like trig involved, or inverse trig, logs, exponential, some non-algebraic functions, or really complicated algebraic function that might take a lot of time to do factoring? That's when L'Hopital's help. So L'Hopital's rule, we introduce this. What does it state? L'Hopital's rule said suppose that f and g, these 2 functions, are differentiable. And the derivative of g of x is not 0 on an open interval I that contains a, except possibly at a. Suppose or let me write it in a different way. Let's say if we are trying to find the limit of f of x over g of x as x approaches a, and we get either 0 over 0 or plus or minus infinity over plus or minus infinity. If we get any of these 2 forms, those are indeterminate. Then L'Hopital said this limit that we are trying to find can be found by finding the limit as x approaches a, derivative of the top, derivative of the bottom one. Not quotient rule. So L'Hopital said just find the limit by differentiating top and the bottom, and then find the limit. So what about if you find the limit and then again you get infinity or 0 over 0? You can do it again. You can say this equals, if you got infinity or 0 over 0, you can do it again. Limit as x approaches a of the second derivative over the second derivative. And then this can go on and on and on. So as many times as you want. If I go back to the same example that I just finished, x squared minus 4 over x minus 2 as x approaches 2. Again, this goes to 0 over 0. Indeterminate. By L'Hopital's rule, L'Hopital said find the derivative of the top, which is 2x, over the derivative of the denominator, which is 1. And then that would give us 2 times 2, which is 4. And that's what we got earlier. See, I don't have to do factoring. I don't have to do think about, any other method. It's just straightforward. We proved also, or actually used this as a theorem. This one is also goes to 0 over 0. And we told you about this before, that the limit of this is 1. Now we can prove why the limit is 1 using L'Hopital's rule by finding the derivative of sine is cosine and the derivative of x is 1. So that would be cosine 0, which is 1. See, that's why. See how powerful this rule is? So what about if I take the limit as x approaches infinity of ln of x over x? So notice here, this is limit goes to infinity, not a number. So again, this will go to infinity over infinity because natural log of x, it goes this way. That's the graph. Graphing is important here. So as this is saying, as x goes to infinity, y goes up, keeps going up and up. That's where that came from. So again, that's indeterminate. So what we need to do is find the derivative of the top. Derivative of ln of x is 1 over x over 1. So now this can be rewritten as 1 over x. Now this 1 over x, the limit of this is a very important function when it comes to indeterminate forms. If I want to graph y equals x, it looks like this one and then this one. So this is the graph of y equals 1 over x. As x approaches to positive infinity, so as we go this way, the graph is approaching y equals 0. If we go toward negative infinity, just for other questions, also goes to 0. If we approach just 0, the limit does not exist because on the right side goes up to positive infinity, left side goes down to negative infinity. So far looks good, straightforward applications. Even if I want to take more, let's say ex as x approaches infinity over, let's say x squared. I was going to do x, but I'm changed to x squared. So this goes to infinity or infinity, indeterminate. L'Hopital's rule tells us the derivative of ex is ex over 2x. Notice if you pass the limit again, that gives infinity or infinity. One more, let's check. Derivative of ex is ex over 2. Where does that go to? Well, again, that's why graphing is important. Ex, that's the graph of ex. Y equals e to the x. As you go to the right side, the graph goes up. So it's infinity. And infinity is okay as an answer for the limit. Let's look at a more difficult example. 0 plus of cotangent x over natural log of x. So let's see. I know I'm going to look at the natural log of x. If I approach 0, this is natural log of x. As I approach 0 from the side, the graph goes down to negative infinity. For cotangent, if you graph it, you will see it goes to infinity. So that gives me an indeterminate form. It doesn't matter if it's only negative on the top or negative on the bottom or both negative or both positive. Same thing. That's indeterminate form. So by L'Hopital's, let's see. The derivative of cotangent is negative cosecant square x. Derivative of natural log is 1 over x. Now if I rewrite this by multiplying by the reciprocal of the denominator, that gives negative x times cosecant square x. Then what is that going to give us? Notice that it's always easier to work with sine and cosine rather than cosecant secant. So rewrite cosecant as 1 over sine. So it's 1 over sine square x. If I pass the limit, that will give me 0 over sine 0, 0. That's another indeterminate form. Indeterminate. So how do I rewrite it, or to get rid of this indeterminate form? I can use L'Hopital's again. So limit as x approach 0 plus the derivative of the top is negative 1. This is 2 sine x cosine x. And in fact, this one, the limit as x goes to 0 plus negative 1 over, this is sine 2x, just to make it easier to see. And if you look at the graph of this, that denominator approaches 0. So this whole thing approaches negative infinity. And you can look at it on the graph to see why this works this way. Note to keep in mind, if we, the first one, limit as x approaches infinity, natural log of x over x to the n. This is always 0. Limit as x approaches infinity, x to the n over e to the x. This is also 0. And they can be both proven using L'Hopital's rule, but good to keep in mind. Now, so far we have been dealing with infinity over infinity, 0 over 0. Is that where L'Hopital can only work? The answer is yes. L'Hopital's rule only works if you have 0 over 0 or infinity over infinity. Okay, but not when we have different indeterminate forms. What about other indeterminate forms? So let's call it indeterminate products. It's called indeterminate products. So indeterminate products, what does it say? We have 0 times infinity and also infinity times infinity. These two forms are indeterminate forms. Are indeterminate, as mathematicians agree to classify them this way. Those are indeterminate forms. So when it comes to some indeterminate form like this means I'm working with a function times another function. That's where we get 0 times infinity or infinity times infinity. And the trick around this is to rewrite it first. Rewrite as f over, like bring one of the functions down, 1 over g, or you can keep the g up there and bring the f down, depending on which one more convenient to bring down. And the reason we do this, because after we pass the limit to this form, the new form, then we are hoping that we're going to get either 0 over 0 or infinity over infinity. Then we can use L'Hopital. So L'Hopital cannot be used straightforward when you see one of these two examples, one of these two forms. And one of the most common examples we use is when we ask to find or evaluate limit x times ln of x or natural log of x as x approaches 0 plus. Well, let's see what that gives us. This goes to 0 times negative infinity, or you can say 0 times infinity. That's indeterminate form. It's not 0. It's not 0. It's classified as indeterminate forms. So what I'm going to do, I'm going to bring one of the functions down. Which function would be easier to bring down? I'm going to keep natural log of x there. I'm going to bring the x down as 1 over x. And for this one, we know from 0 plus, this is negative infinity. And the same thing for this one. If you graph it, if you remember, you got approaching 0 plus, then this is infinity. Okay, from the right side of 0. So that's indeterminate form. But the difference between the previous line, the line above this, and this one, here I can use L'Hopital's rule, but not on the line above it. So 0 plus, the derivative of natural log of x is 1 over x. And if you find the derivative of 1 over x is negative 1 over x squared. Don't pass the limit yet. What we need to do is try to simplify algebraically this mixed fraction. This is a division sign. We can switch it to multiplication and flip the fraction, like so. And let's see what we get. X goes to 0 plus of negative x. Substitute that in, we get 0. And 0 is the answer. Now you can, if you like to bring the natural log of x down, that's fine too. No problem with that. That's totally fine. What about if we look at a more difficult example? Say x goes to 0 plus of sine x times natural log of x. So how do we do something like this? If you pass the limit, this is 0 and this is negative infinity. So that's an indeterminate form. But I can't use L'Hopital. I have to bring one of the functions down. So how do I do this? Let's say I'm going to bring, we always keep the natural log of x up there. Bring the sine as 1 over sine. But before I find derivatives on this or pass the limits, other thing good to do here is this complicated fraction 1 over sine, let's write it as cosecant. And if you look at the graph of this one, that's negative infinity over infinity. So what we need to do in this case, is to use L'Hopital's rule. L'Hopital on the top one is 1 over x. And the derivative of the denominator is negative cotangent cosecant. And let's see what we get in this case. That's gonna still give us some issues here. What about if I bring it down, bring the x down? So it's like 1 over negative x cosecant x. You can say multiply top and bottom by x, just in case. Multiply by x and by x. That's why the x went down in the denominator. That still gives me indeterminate form in the denominator. So I don't want to do L'Hopital again, because notice how the top will be 0 but the bottom is not, and at the same time the denominator is not even 0 when we pass the limit. So I can't use L'Hopital because it's not 0 over 0 or infinity. So one thing I can do, as I said earlier, mentioned that I can convert things into sine and cosine. So this is cosine x over sine x. And then I'm going to try to simplify this. So limit as x goes to 0 plus. Here we got sine square x on the top, and the denominator negative x cosine x. So now if you pass the limit, that's really 0 over 0. Indeterminate, I can use L'Hopital's rule. So L'Hopital's rule said you can take the derivative of the top, which is 2 sine x cosine x. And the denominator, what we do is keep the negative out. 1 times cosine x plus x times negative sine x. So then the limit as x goes to 0 plus, let's see what we have here. Can we simplify anything? Nothing can be done on the top, unless if you want to do it sine 2x. Denominator is just negative cosine x plus x sine x. If you pass 0 in, if you pass the limit to this, let's see what we get on top. 2 times sine 0 is 0, so that's a 0 on the top. Negative cosine 0, that's a negative 1 plus 0. Oh, the answer is 0. Done. So we had what we've done so far. We got one of the forms is called indeterminate products. And here, this one's like indeterminate quotients, let's call it. You know, the one we got 0 over 0 or infinity. Those indeterminate quotients. And now we have what we have next, indeterminate differences. Indeterminate differences. So indeterminate differences. So indeterminate differences, that's when we get infinity minus infinity. That's not a 0. That's an indeterminate form, because each infinity here represents a different huge number. So it could be the first one bigger than the second, or the second bigger than the first. So we don't know which one is which. Usually this happens, the trick to get rid of this, or to be able to solve something like this, usually this occurs when we have fractions. And in case we have fractions, the key to solve this is to combine. Why do we combine them? Because when we combine them, we get one fraction, hoping we're going to get, again, 0 over 0 or infinity over infinity. And in that case, then that makes things easier for us, because then L'Hopital's rule can be applied. So let's look at this example so you can show you how. X approaches 1 plus 1 over natural log of x minus 1 over x minus 1. So what's the limit of this? So we know this goes to 1 over natural log of x. You can, if you graph this, you're going to see that this goes to infinity. And the second one, just so you see, like you got 1 over 1 minus 1, 0. So, but that thing has a graph like this, like that. So if you approach it from, this is 1 here, from this side it goes up to infinity. So infinity minus infinity, which is indeterminate. So we get an indeterminate form. Again, one of the keys, as I said, is to combine the fractions by finding the least common denominator, which is x minus 1 times natural log of x. And you get x minus 1 minus natural log of x. Then what do we do next? We are going to find the derivative of the top, which is 1 minus 0 minus 1 over x. Derivative of the bottom is derivative of the first one, which is 1 times natural log of x, plus the first one times the derivative of 1 over x. So I use product rule in the denominator. Let's see what we can do next. On the top, I have 1 minus 1 over x, denominator ln of x or natural log of x, x minus 1 over x. Those are complex fractions. The easiest way to finish this up is to multiply this by x, by x, by x, and by x. That will clean up the fractions, makes it simple fraction. X minus 1, x natural log of x plus x minus 1. Now, if we pass the limit to this, what do we get? On the top, we get 0. This is 0, and natural log of 1 is 0. Oh, again, indeterminate. We need to do L'Hopital, apply L'Hopital's rule again. So let's see what we get. Limit as x goes to 1 plus. Derivative to the top is 1. Here we have to use product rule on this one. 1 times natural log of x plus x times 1 over x plus derivative of x is 1. So what do we get here? Natural log of, the limit as x approaches 1 plus 1 over natural log of x plus 1 plus 1. So this goes to 0, and that will give us 1/2. That's the limit. Note, sometimes you can factor something out, like factor the heaviest term. If you have two things but you can't combine them, you can factor the heaviest term out, and that will help you to solve this kind of questions or problems. Now, what about the next form? Is called indeterminate. Indeterminate powers. So indeterminate powers. The one before this was indeterminate differences. So we have quotients, differences, product, and powers. In powers, we have several ones of them. Several ones. One of them is infinity to 0. That's an indeterminate form. 0 to 0. That's another indeterminate form. 1 to the infinity. That's an indeterminate form. So far we have how many forms? Let's count them. We started with 2 of them that we already seen before in previous sections, 1, 2. And then we got to the infinity times 0 and infinity times infinity. That's another 2. That's 4 of them. 4 of them. And then we have infinity minus infinity, 5. And the last 3 here, those are 3 of them. We call them powers. Infinity to the 0, 0 to the 0, and 1 to the infinity, the 3 of them. Now, the good thing about all these 3 forms, they follow the same procedure, the same strategy. That's why we show the strategy to all of them by using, just one strategy that fits all of them. And the way this works is that probably, let's say we're finding the limit as x goes to a of a function times, so raised to another function. Okay, and then you got one of these forms. What makes these forms difficult to work with by having these zeros on the top or infinities. And to simplify that out, what we do, we let y equals this function f of x to g of x. And then the reason we use this because we can do L on both sides, and that's the easiest way to bring that function down. Okay, so that's how we start with this. Then after we do this, then we pass the limit. And see what happens on the right side. Like, do we get infinity over infinity, 0 times infinity, and then we just finish it from there based on the problem that we have. Note and recall this: if ln of, let's say, y equals m, then don't forget that the base is e here. E to the m is y. This is important here to keep in mind. So let's look at an example here. Let's say we're asked to find the limit as x approaches infinity of x to 1 over x. The top one, as you see, the denominator is infinity. The top is 1 over infinity. Like the graph passes, when you approach 1 over x from the right side, like as x goes to positive infinity, that goes to 0. So that's one of the indeterminate forms, the first one. So then what we do, as I said earlier, we let y equals x to 1 over x, and then natural log both sides to bring the 1 over x down, which can be rewritten as natural log of x over x. When we pass the limit now, as x approaches what was the original one? Infinity, equals limit of natural log of x over x as x approaches infinity. Look at the left-hand side. The left-hand side, it's, you can say it's just, you can leave it like this, or you can, there's no axis, you can drop the limit, but let's keep it for now. This one goes to infinity over infinity. So what I can do on the right side, I apply L'Hopital's rule on the right side, which is 1 over x over 1. So that's the limit as x approaches infinity of 1 over x. And that's really 0. Now, a lot of people, they think 0 is the answer. It's not. We would like to find the limit as y go, the limit of y now. See, because this is y. But I didn't do y. I found the limit of ln of y. Do you see that? So it's the limit of ln of y. Then, what is it here? So then I'm trying to find the limit one more time of x to 1 over x. Right, as x approaches infinity. So that's basically the same as the limit as x approaches infinity of y. Right? Of y. But y, you can write y as e ln of y, e natural log of y. Because e natural log of y is y. And the natural log of y, we found, if you pass, you can pass the limit there as x approaches infinity of natural log of y. The natural log of y, we found it's 0. So this is e to the 0, which is 1. So the answer is 1, not 0. We may look at more examples on this. Let's say I want to find or evaluate the limit as x approaches infinity, ex plus x to 1 over x. What we do here, we let y equals e to the x plus x. Again, this is infinity plus infinity to 0, infinity to the 0. So we let this equals to y. Natural log both sides, and that would be natural log of e to the x plus x all over x by bringing that 1 over x down. Limit as x goes to infinity. Equals limit as x goes to infinity of the natural log. It's important to show steps. Those steps are important. So we get the limit as x approaches infinity of natural log of y. This one, what happens? Let's see. Infinity ex E infinity, infinity plus infinity. Ln of infinity is infinity or infinity. We can use L'Hopital's rule on the right side. The derivative of ln of u, it's u prime over itself over the derivative of the bottom. So x goes to infinity of natural log of y equals limit as x approaches infinity. No, this is x. So if we pass this, what do we get? We get infinity on the top over infinity plus infinity, infinity. So another indeterminate form. So we keep the left hand side the same, like so, equals limit as x approaches infinity, ex over ex plus 1. And guess what? Again, infinity or infinity. So that's the good thing about L'Hopital. You can use it as many times as you like. X goes to infinity, ex over ex. But ex over ex is 1. So I'm basically finding the limit of 1 as x approaches infinity. And that's 1. But keep in mind, the answer is not 1. Okay, so we're going to go back and say, okay, what I was trying to find? The limit of ex plus x to 1 over x. So what is it? Remember we said this is y. The whole thing, we assumed the whole thing is y. And this can be rewritten as e ln of y. Okay, e ln of y. And now you can move the limit up like this. And then e to what? What's the limit of this? We found it here on this line. It was 1. So we get e to the 1, which is e. So that's the answer. E to the 1 is 1. What about if we are asked to find the limit as x approaches 0 plus of 1 plus x to 1 over x? Similar to the previous one, but this will be different. So if you pass the limit 1 plus 0, it's 1. Okay, so that goes to 1. 1 over 0 plus as a limit, that's infinity. It's not 1. This is not 1. This is indeterminate. It's an indeterminate form. Again, same procedure. Y equals 1 plus x to 1 over x. Natural log both sides. That will allow us to bring 1 over x down. Limit of ln of y as x approaches in 0 plus. X approaches 0 plus. Natural log of 1 plus x over x. This goes to what? 1 plus 0 is 1. Natural log of 1 is 0. So that's 0 over 0. Indeterminate. The good thing about this step is that I'm allowed to use L'Hopital's rule here. So natural log of y stays as is. Here, by L'Hopital's rule on the right side of the equation, that gives me 1 over 1 plus x over 1, which is 1. Then, what I'm trying to find, the limit as x approaches 0 plus of 1 plus x to 1 over x equals limit as x approaches 0 plus of y, right? Of y. But y can be rewritten as e natural log of y. And then the limit on the top one, we found it. It was 1. So you get e to the first power, which is e again. These are all the indeterminate forms for this section. We have 8 of them, total 8 of them. And then, as I said, each one of them has a trick. The first 2 were straightforward. If you get 0 over 0 or infinity over infinity, you use L'Hopital's rule. If not, if it's a product, you have to rewrite it as a quotient. So you can get 0 over 0 or infinity over infinity. And if it's a difference, then what you need to do is combine the fractions or factor something out. And then if it's in the form of a power, then you let that thing to be y all the time, and then natural log both sides to bring the exponent down.